Good afternoon, everybody. Good. All right. So the gentleman pictured on the right side of the screen there was Rick Smalley. Rick Smalley won a Nobel Prize in chemistry a while back for discovering some cool molecules called fullerenes, which look like little molecular soccer balls. But more importantly, for the purpose of this conversation, he devoted the later years of his life. He unfortunately passed away at a premature age due to terminal disease, but very smart man. He devoted the later years of his life to focusing on the biggest challenges that we face as a society over the next 50 years. And he really invested in this and redirected his entire career towards it and came up with this list of the top 10 challenges that we face. And they're actually in order from top to bottom. That doesn't mean that the ones at the top are necessarily more important than the ones at the bottom, but if you can solve the problems towards the top of the list, it helps you solve the problems towards the bottom. So to give you one example of that, you notice population is at the bottom of the list there, number 10. We have a problem with unsustainable population growth on our planet, currently 7 billion and rising. And it's been well established that if you can improve education in the developing world, particularly of women, birth rates go down, which helps us solve the population problem. So if you solve the education problem, helps you solve the population problem. And you'll see way at the top of this list is energy. So at least according to Rick Smalley's analysis, this is the single biggest challenge that we face over the next 50 years. To give you one more example of the connectivity, you'll notice number 2 on the list is water. We have increasing water scarcity, freshwater scarcity that is on the planet. We know how to turn salt water from the oceans into fresh water. It's a process called desalination. But to do desalination, you need a lot of energy. So if you solve the energy problem, it helps you solve the water problem. So this plot here kind of shows you why we're feeling so much strain in energy in all these other areas too. This is a plot of our population worldwide. Starting back in the 1800s, we had about 1 billion people on the planet. And also each of those billion people was not using a whole lot of energy individually. But that population really started to grow dramatically. In the 50s, it was a few billion. And as I said, now we're at 7 billion, but you can see the curvature of that plot. It's upward trending. We're growing fast. And we're also using more energy individually. So the energy demand is increasing dramatically. You can see that here. So this is a plot of how much energy we use worldwide each year. And the units that you see there are TW, terawatts. A terawatt is 1 trillion watts. It's a lot of watts. So a trillion is 1,000 billion. So you think about the light bulb you screw into the socket at home, that's maybe a 25-watt light bulb. So picture trillions of those, right? That's how much energy we use worldwide, massive amounts of energy. And you notice that it's more every year than the year before. So here I'm showing 1990 to project it out to the year 2035, but you can go back further in time and it was less every year as you go back in time, and you can go past 2035 and it keeps growing going into the future. And you can see where most of that growth is coming from because I've broken this plot down. The dark blue part of those bars is the developed world. That's places like the United States, Europe, Australia, and so on. The light blue part is the developing world. That's places like China, India, Brazil, Africa, for example. And as you look forward in time, you can see where this growth is coming from. It's almost entirely in the developing world. That's because they're developing. These are parts of the world where people didn't necessarily have air conditioners or cars or computers or light bulbs even. And so as they begin to develop, these people use more energy, and that dramatically increases the overall global energy demand. So just a few numbers to keep in your head. Today, we use energy at a rate of 18 terawatts. You can see it right there on the graph. That's where we are today at 18 terawatts. By the year 2035, that'll be about 25 terawatts. And if I kept plotting this out to the year 2050, it would be 30 terawatts. So today it's 18. By the year 2050, it'll be 30. That's almost twice as much energy. So the question is, where are we going to get all this energy from? Let's start with today. Let me ask you guys, where do we get most of our energy from today? Coal's number 1. What else? Oil, that's a big one. What else? Methane, natural gas, that's the third. 1, 2, 3. Coal, oil, natural gas is where almost all of our energy comes from. Fourth on the list would be nuclear. But it's almost all fossil fuels. I'll show you the data a little bit later in the talk. One more question for you, and then I'll do the talking. Why do we get almost all of our energy from fossil fuels? Cheap. It's cheap. That's why we get almost all of our energy from fossil fuels. There they are, coal, oil, and natural gas. What I want to convince you of is that that energy that seems really cheap, those fossil fuels, are actually costing us a lot more than we think they are. You are spending more money out of your paycheck to use that energy than you realize. So you know what you pay the electric company, and you know what you pay at the gas pump when you fill up your car, and you know what you pay the gas company if you have natural gas in your home. But you're paying a lot more than that to use that energy, and I'll explain what I mean soon. But I want to draw your attention to this report. It's actually available for free online. It's published by the National Research Council, a bunch of smart scientists here in the United States. And what they wanted to do is actually quantify these hidden costs associated with energy, this money that we're spending that we don't realize. And in their analysis, the number that they came up with, first of all, they only looked at the year 2005. The report came out in 2010, and that was when they had the best data set, was for the year 2005. And they were only looking at the United States, because we're talking about the National Research Council of the United States. So we're only talking about one country in 1 year. And in their analysis, they did not include, for example, the costs of climate disruption, climate change. Not because it's not a massive hidden cost, but there was too much uncertainty in the number, and they were trying to come up with a relatively firm number in this report. So they mention it, but they don't put a number on it. They also don't include, for example, the costs that we spend on our military overseas, securing fossil fuel resources, for example. We fight a war in the Middle East to liberate Kuwait. That's obviously not because the Americans necessarily are particularly invested in the livelihood of Kuwaitis. It's because they have fossil fuels, right? So none of those costs are in there either. So we're not including climate disruption in there or costs like those military expenditures. And even without those, and just in 1 year, just in the United States, they came up with a number of $120 billion with a B. So we're talking about a pretty big chunk of change here. So where do those hidden costs show up? Some of them aren't so hidden. You see them on the front page of the paper. In fact, there is a front page of the paper. So I have one example here from each of our major sources of energy. We've got oil, gas, coal, and then I added in nuclear, which, as I said, would be sort of number 4 on the list. And these are disasters. So you probably all remember the BP Gulf oil spill a few years back, which was the largest oil spill in history and was a massive ecological disaster. The costs associated with that, well, BP, we know, has had to pay out something like $40 billion, deal with the government and so on, because of the damage caused by that spill. The cost is probably larger than that. We all end up bearing that cost, but we don't necessarily pay it at the gas pump. For example, we had to pay EPA workers and Coast Guard workers and all kinds of people to go down there and address this. We pay that with our tax dollars, right? So we're paying it, but we're not paying it at the gas pump. That's why it's a hidden cost. And of course, these things happen all the time. That was just the largest such example. Just in the news, the timing is good. Santa Barbara, just this past week, there was an oil spill off the coast of Santa Barbara. And there are countless other examples. These things happen all the time. It's inevitable when you work with oil. Natural gas, when you have a disaster, if you will, the natural gas, usually it doesn't make the front page of the national news because maybe there's a leak in a house or something like that, and they might have an explosion in a house, but that's not, doesn't show up on CNN. But sometimes you have a larger problem, like this photo here is taken from San Bruno, that's the part of San Francisco near the airport there, when a gas main blew up, 16-inch gas main. You can see by the time the news photographer got there, it looked like that. It was probably even worse beforehand. And this was quite a calamity. This destroyed a good section of a neighborhood there. We're talking about cars, homes, businesses, people injured, and so on. All of those things have costs associated with them. Those have car insurance, home insurance, business insurance, life insurance and health insurance. We pay for all those things through our insurance. That's how insurance works, right? We all have policies, we pay into them, and then when there's a payout, it comes out of that pool. So we're all paying for it, but we're not paying it to the gas company. Hidden cost. Coal hits home for me. I grew up in western Pennsylvania, and there's a lot of coal mines around there. So I knew people who, growing up, who were associated with coal mining. This example comes from Turkey. It's one of the more recent ones where there was a coal mine disaster where these things happen from time to time, where there's a collapse or an explosion inside the coal mines. In that particular incident, I believe it was around 300 miners lost their lives. So, I mean, there's some economic cost with that, but we're also talking about just a human cost, right? These are people dying because we're using that coal. If we weren't burning that coal, these guys wouldn't have been under the ground. And again, those things happen all the time. There's been disasters, not quite that large, but similar in West Virginia and in South America and all over the place. Now, nuclear, we heard all about nuclear energy from Helen Caldicott this morning, so I won't dwell on that. In general, it's actually quite a safe form of energy while they're operating, but you have challenges like what to do with the high-level waste. You have challenges like proliferation of the materials, and once in a while, not often, but it's a big deal, you have a disaster, like, for example, what's shown here, the Fukushima Daiichi disaster a few years ago, where there was the tsunami that caused the major meltdowns there. The cost for that will probably be something more like $1 trillion, and will take at least 100 years to clean up if they can ever clean that up. So we're talking about a pretty massive, massive cost, and that's not being paid by on the electric bill of the people in Japan. It's being paid really by all of us. Other examples. So when you burn coal in a power plant, all kinds of stuff comes out of the smokestacks. Some of those things are sulfur dioxide and nitrogen oxides. And when those things mix with the water that's up in the air, you get sulfuric acid and nitric acid. And then it rains, and that comes down as acidic rain, acid rain. And when acid rain hits things that are made out of metal or certain types of stone, for example, they degrade, they'll dissolve and rust. You can see a picture here of a bridge, for example. So because of acid rain, our infrastructure degrades more quickly than it should otherwise. Bridges need to be repaired and rebuilt earlier than they would have to be otherwise. Cars need to be replaced or repaired and so on. We're all paying for that, right? Our tax dollars repair those bridges. We're paying directly for repairs to our cars and so on, but we're not paying it to the electric company who's burning the coal. That's why it's a hidden cost. Other stuff comes out of those smokestacks too, like particulates and ozone, and I'll explain where those costs come in a moment. Heavy metals as well. Inside the coal are heavy metals like mercury, for example. You burn it, they try and capture some of it in the smokestacks with some pollution control technology, but they don't capture all of it. Some of it comes out of those smokestacks. It tends to collect in water, and then there's things that live in the water that end up taking the mercury inside them, and if we eat those things, it ends up inside us. So where do these things show up as costs? One would be health insurance. We now all have health insurance, Obamacare, right? And so we're all paying money for health insurance. And when someone gets sick, again, we all pay for that, right? Particulates and ozone cause asthma attacks. I've given talks to school groups and teachers from the Pilsen neighborhood in Chicago, where there was a coal power plant that just fortunately actually was shut down about a year ago. But they told me when I would present it to them that almost every day in their class, they would have a kid who was either having asthma in class or was actually out of class because of asthma attacks. There are tens of thousands of asthma attacks caused by these particulates and ozone. Those people end up in emergency rooms. You know what it costs when you go to the emergency room. That's not cheap. And again, we're all paying for that. But we're not paying it to the electric company. I mentioned food. That mercury that ends up in the water ends up being bioaccumulated in fish is a big place where it goes. Some fish more than others. Swordfish is a particular problem, but there are plenty of other examples. If you're a pregnant woman and you ingest that mercury while you're pregnant, your child's much more likely to have developmental disorders. That translates to a whole lifetime of hidden costs. And there are all kinds of connections to water beyond that. There's actually energy and water are so interrelated that I could spend an hour and a half just talking about that. Don't worry, I won't. But one example that I'll give is something called thermal pollution, because a lot of people don't know about this. So the way these power plants work, it doesn't matter whether they're coal or nuclear or natural gas, they all work the same way. They're sited near a large source of water, like a lake or a river, and they bring in massive amounts of water, like hundreds of billions of gallons of water a day, massive amounts of water. And they boil that water by burning coal or using the heat from the nuclear fuel or whatever to make steam. And then that steam turns turbines and that makes electricity. That's how power plants work. But what you have on the other end of that power plant then is hot water, which gets shot back into that lake or river or wherever it came from. And so what they're doing is they're constantly heating up the water, making it hotter and hotter. And hot water cannot dissolve as much oxygen as cold water. It actually pushes the oxygen out of the water. And so things that live in the water and need that oxygen don't have it, and you get sort of dead zones near the effluent of these power plants because they're ejecting water that's too hot for the local ecosystem to thrive. The biggest hidden cost associated with our use of energy, though, is this one, global warming. Now, I actually try not to use this term, global warming, and the reason I tend to avoid the term is when I hear the word warming, I picture something like this. Warming sounds cozy and nice, and you're wrapped in a blanket, right? And what we're doing is not cozy or nice. It also sounds benign and gradual. The term you often hear is climate change. Technically, actually, from a scientific perspective, these mean different things. Global warming is referring just to temperature. Climate change is much more than just temperature. But I also am not a big fan of the term climate change, because probably this isn't so familiar to folks here in Orlando, but up in Chicago, where I'm from, by the time February rolls around, it sounds like maybe some climate change isn't such a bad idea. The term that I prefer is this one, climate disruption. And this is not my term. This term was coined, I believe, by John Holdren, who is President Obama's chief science advisor, smart guy, professor from Harvard. And the reason that he chose this word disruption is it really captures the fact that we are taking a system that was more or less stable and we're throwing it out of whack. We are actively throwing it out of whack. And it's not benign or gradual, it's a big problem. We are disrupting it. It's not just changing. Change can be a good thing, right? There have been presidents elected with the phrase change. Disruption is not a good thing, at least not in this context. And so I draw your attention to our book that I wrote. So I'm not a climate scientist, but my co-author is, Doug Sisterson. And together we wrote this book called How to Change Minds About Our Changing Climate, where we've really tried to address sort of the basics of climate disruption so that people can understand that. But more importantly, there's a whole bunch of misinformation out there, that it's not happening, that it's not caused by us, that it's not something to worry about, and so on and so forth. I'll get into some of that in a moment. But what this book does is it really goes through each one of those, what I'll call myths, one at a time, and explains why they're not based on science, why they're not accurate. And it does it all without equations or anything. I have a 12-year-old, and I think he can read it and understand it all. So hopefully everyone can as well. So where do the problems of climate change come in, climate disruption? One example would be the melting of glaciers. We heard about this from John Eglander earlier today. So this is a problem for all sorts of reasons. So you warm up the planet, glaciers melt, right? And one of the things that leads to, as we heard from John this morning, is sea level rise, which is a pretty massive concern, particularly if you have coastal property, if you live in Miami or New Orleans or any other low-lying area. There's another reason it's a massive problem, though. There's a large fraction of people on the planet who get their water, the fresh water that they drink and use every day, from the meltwater off glaciers. When those glaciers are gone, where are they going to get their water from? I actually don't know. They're going to have to move, probably, because water is not something you can move from one part of the planet to another on a massive scale. It's just too big and heavy, and you need too much of it. You've got to be where the water is. And so that's going to be a major challenge as we go forward. Another example of how climate disruption is causing a problem is what's called ocean acidification, and this is another one of those things that not as many people are aware of. So what we're doing when we burn these fossil fuels is we're putting carbon dioxide into the atmosphere, and the stuff that stays up in the atmosphere increases the warming of the planet, which is a lot of what we talk about when we talk about climate disruption. But a lot of that carbon dioxide ends up in other places too, and one of those places is the oceans. The oceans absorb massive amounts of carbon dioxide, and when you put carbon dioxide into water, you get carbonic acid. And so that makes the ocean more acidic. The ocean is actually slightly alkaline, slightly basic, but you can measure that pH over time, and the pH has been going down for a very long time, meaning it's been getting more acidic for a long time. So why do we care about that? We care about it for lots of reasons. One is what's pictured here. That's a coral reef, or I should say was a coral reef. It's experienced what's called coral bleaching, which doesn't sound so bad. Coral death would be a better word. Basically, coral can't survive in this more acidic water. And so they die. And coral reefs are one of the most biodiverse places on our planet. So we're really destroying the biodiversity of the marine ecosystem. And it's also, in large part, the base of the marine food chain. So this is a pretty massive problem when coral reefs start to die, and indeed they are starting to die from this effect as well as other pollution caused by us. Another challenge would be shellfish. Mussels, oysters, things like that. Their shells are made of calcium carbonate. And when you make the water acidic, it scavenges those carbonate ions. They can't grow their shells as easily. You can think of it as dissolving their shells. And so shellfish populations are actually dropping already. For example, off the Pacific Northwest coast, fishermen are seeing that there, that populations of these different species are already starting to drop. Another example here would be polar melting. So the effects of climate disruption are generally felt most strongly at the poles, which is a little bit unfortunate for getting the message out because people don't live at the poles, and so people don't see what's happening up there unless you happen to watch a documentary about it. But this is a big deal, and it's something really to worry about. And one of the biggest concerns here is what we call positive feedback cycles. And this isn't positive in the sense of a good thing. It's positive in the sense that something that feeds back on itself and makes it stronger and stronger. So two examples from the Arctic in this example would be sea ice. So the Arctic has a lot of sea ice, and it has been melting progressively because of warming of our planet. And that's a problem if you're a polar bear, but I'm not sure how much we should or should not care about polar bears. That's not necessarily the biggest concern here. But the sea ice is white. And so sunlight coming down hits that white sea ice and gets reflected back up without warming up the planet very much. But when the sea ice melts, you have ocean, which is dark and absorbs lots of that energy coming from the sun and heats up more. When it heats up more, it melts more sea ice, so it absorbs even more energy, which melts more sea ice and so on, and it builds on itself, accelerating the problem. Same goes with what's pictured here. This is a picture of the permafrost up in the tundra in the Arctic. And in that permafrost are massive, massive amounts of methane, natural gas, frozen in the ground. Enormous amounts of methane. And it's been frozen there for a long time. But when it melts, it comes out, and that methane goes up into the atmosphere. And we talk about carbon dioxide a lot as a greenhouse gas, but methane is a much stronger greenhouse gas. So we're releasing all this methane, it's going up into the atmosphere, causing more warming, because it's a strong greenhouse gas, which melts more permafrost, which puts more methane up, and again, you have a feedback cycle. Really scary. Another place where climate change causes us trouble is in extreme weather. We're already seeing people ask, how come I don't see climate change out there? You do. We are seeing increasing occurrences of extreme weather. There are 100-year storms happening every 5 or 10 years now, so they're not really 100-year storms anymore. There was that set of like 2 or 3 massive snowstorms we had, what was that, about 8 or 9 years ago, Snowzilla and Snowmageddon and whatever they were called. And these things are happening all over the place. We're having stronger hurricanes. When those hurricanes hit a massive populated area, like Hurricane Katrina in New Orleans, Hurricane Sandy in the New York, New Jersey region, that causes hundreds of billions of dollars of damage and, unfortunately, loss of human life as well. We all pay for that, right? That's coming out of our paychecks, but it's not going to the coal-burning electric company that put all the carbon dioxide in the atmosphere, which caused it in the first place. Another connection would be through agriculture. So some of that extreme weather would be bigger droughts. We have one in California right now, right? And this has been happening more. More severe droughts, deeper droughts. Australia had a massive one about a decade ago called the Big Dry that wreaked havoc down there. We're also having more flooding. Farmers like water at the right amount. They don't want too little and they don't want too much. Both of them wreak havoc on agriculture, and both of those are happening more often. We're having more flooding as well. That makes us pay more for food. And unfortunately, for some parts of the world, it will mean there's not enough food. So I mentioned sea level rise earlier. So melting of land ice, that land ice added to the ocean, puts more water in the ocean, sea level rise goes up. We heard a beautiful presentation about that from John this morning. It also rises, as he nicely explained, because of thermal expansion. When you warm up objects, they expand. If you have a balloon and you blow a hot hairdryer on it, it's going to expand. Same thing with the oceans. They get warmer, they literally get bigger. So the ocean is getting bigger, and we're adding water to it, both of which are causing sea level to rise. This is a major concern for the huge parts of the global population that live near coastlines. That is a good example of the kind of ways that this is going to result in security costs for us. So when you have massive migrations of people, which is what's going to happen when you have, for example, starvation because agricultural problems in subsistence farming regions of the world, or when you have sea level rise flooding some of our major cities, you have massive numbers of people moving from one region to another, and that is not a good thing for geopolitical stability, and this is going to cost us a fortune. And the last example on here would be health, which I guess for this crowd is maybe the most relevant. So there are many ways in which health will be impacted by this, but one good example would be insect vector-borne diseases. So insects like mosquitoes are starting to migrate to regions where they didn't have a good foothold before. And insects like mosquitoes carry all sorts of diseases, dengue fever, West Nile virus, malaria, and others. And so as those populations spread, those diseases spread over a large scale and afflicting countless numbers of people, which is a massive global health cost for all of us. So let's take a step back and look at some of the science. Why does the climate get disrupted? Why does it get warmed up when we put carbon dioxide in the atmosphere? So This is because of the greenhouse effect. This is a figure right out of the book. So for those who aren't familiar, let me just quickly explain what is the greenhouse effect. What are greenhouse gases doing? So the sun is shining down on us with lots and lots of energy. I'll even show you those numbers, how much energy that is a little bit later. And that warms up the Earth from the sunlight hitting it. And then the warm Earth radiates that heat back up as what's called long-wave radiation, or it's in the infrared region of the spectrum. Radiates it back up towards space. And if we had no atmosphere with no greenhouse gases, that would just go right back up into space. But luckily for us, we actually do have an atmosphere. We wouldn't be here without it. And the greenhouse gases in the atmosphere trap some of that long-wave radiation. They actually absorb it and send it back down to Earth. And they also send some of it back up into space. That's the greenhouse effect. It's just a blanket around the Earth, basically, capturing this heat that would otherwise be escaping to space. So it's a good thing. If we didn't have those greenhouse gases, this would not be a livable planet. We need them. And what they do is they allow our planet to be, on average, if you look across the entire planet, about 60 degrees Fahrenheit. So obviously in a given location, the temperature varies wildly, and some locations are warmer than others, but if you look across the whole planet, it's about 60 degrees Fahrenheit. If you took away those greenhouse gases, the planet would be about 0 degrees Fahrenheit on average, which would not be very hospitable for us, or many other things. So we would basically be a dead planet if we didn't have those greenhouse gases. You can just look at some neighboring planets like Mars, which has lost most of its atmosphere, and it's not a very hospitable place. Now, what's amazing is that massive effect from 0 degrees up to 60 degrees Fahrenheit is actually caused by a really tiny amount of gas in the atmosphere. So this shows you what our atmosphere is made of. The circle on the left is the whole atmosphere, and you can see it's almost all nitrogen. The vast majority of our atmosphere is made of nitrogen, which is not a greenhouse gas. The next biggest gas would be oxygen, which is very important for us, but not a greenhouse gas. And that tiny little sliver you see there of what's left is what's blown up on the side there. And that tiny little sliver is mostly argon, also not a greenhouse gas. That's just an inert gas in our atmosphere. And only that tiny little sliver of the tiny little sliver is the greenhouse gases like carbon dioxide, and there are some dozen or so other greenhouse gases. Methane would be another example. So it's really a minuscule fraction, 0.05%, less than 0.05% of our atmosphere made up of these greenhouse gases. And yet they have this massive effect on our climate. And what that tells you is that a little bit of greenhouse gas goes a long way. They're really powerful. So you can look at how they can affect our climate by going back in the ice cores, and we saw some of this presented earlier. What an ice core is you go to a glacier, you can go to Antarctica, and you dig down into the ice, and you core it out. You pull out a section, a cylinder of that ice from a nice deep hole. And what that gives you is a historic record of what Earth was like dating back for a very long time into the past, because what makes up these glaciers and the land ice in places like Antarctica is snowfall every year. You get some snowfall, it gets compacted down, and then the next year it snows on top of that and gets compacted down, and they just build up on top of each other. And so you get layers, and you can see there that in that photograph the layers. Each one of those stratum is 1 year. And what's amazing is that trapped inside that ice is the actual air that was on Earth at the time that snow fell down. And this goes back for hundreds of thousands of years. So there's air that was trapped hundreds of thousands of years ago in tiny little bubbles inside that ice, and it's still there. And so you can dig down, pull it out, and sample it, do some spectroscopy on it, and actually measure what is the composition of that air, how much carbon dioxide, for example, was there in it. You can also pull out what the temperature was from these data, because there's different isotopes in there that allow you to do that. And so we have pretty good data going back much further than I show here. We actually can go back about 800,000 years with these ice core data and show the temperature on the planet and the carbon dioxide in the atmosphere. And those data are shown here from one of these ice cores, and the particular one shown here is the Vostok ice core. You can see here in the red is the temperature, and in the blue is the carbon dioxide. And you don't have to be a scientist to look at those and say they're obviously correlated with each other, right? And that's not surprising. This is what we would expect. Carbon dioxide is a greenhouse gas. You put more of it in the atmosphere, it's going to warm up. You take some out, it's going to cool down. And they've been tracking each other for a long time. And if you look at this carefully, you can see it looks like there's a bit of a cycle there. About every 100,000 years, you get this up and down nature to it, right? So why does that happen? Where does this natural variability come from? And I'll show you that, but first let me point out, look at the scale here for the concentration of carbon dioxide in our atmosphere. The units are ppm, that's parts per million. So again, we're talking about tiny amounts of gas. But you can see the entire history shown here ranges between about 180 and about 300 parts per million. Never went above 300 parts per million in that history shown there, 300,000 years. And in fact, it never went above 300 ppm if you go back 800,000 years, or even longer. That was the maximum, was 300. Keep that in your head for a second. So why did we get these cycles, though? Why does the temperature on our planet change like that? It has to do with something called the MILANKOVITCH cycles, named after a guy named Milankovitch. And what he figured out, he was actually under house arrest during a war in Europe, and so he had a lot of time to think. And he figured this out, that the Earth changes the way it goes around the sun very slowly over time. It changes the angle, it wobbles around, the shape of the orbit changes. They're not big changes, they're subtle changes, but a little bit can make a big difference. And the time scale of that is tens and hundreds of thousands of years, and that's what causes that cycling that we see in the deep ice core. So even if were never on the planet, the temperature would change, but the time scale of that would be tens and hundreds of thousands of years, not decades. And then we came along. So it was doing that happily between 180 and 300 ppm back and forth for about 100,000 years, and then we started taking this fossil fuel out from under the ground, which has lots of carbon in it that was trapped in the oil and gas and coal for millions of years, and we burn it, and that puts that carbon back into the atmosphere, the carbon dioxide back into the atmosphere that had been trapped all that time. And so we should see that the carbon dioxide concentration in the atmosphere will be going up if we're adding carbon dioxide. And it sure is. These are data taken from Mauna Loa. And you can see that's the carbon dioxide concentration by year from 1960 or so up to the present day. And you can see it just keeps marching up. And it's marching up because we keep adding carbon dioxide to the atmosphere by burning fossil fuels. Notice the numbers, though. Look where we are today. We're at 400 ppm today. That's 100 more than it has been for, in fact, millions of years on Earth. And if you go back to the last time we had this type of concentration of carbon dioxide in the atmosphere, Earth was a very different place than it is today, and not very hospitable to modern society. So this is a big concern, and that's where we are today. That's still going up. So carbon dioxide goes up, temperature goes up. Here's the temperature data. So there's all kinds of different ways to measure temperature around the Earth and aggregate that data, and here's various different measurements of that, and you can see from, here shown from 1950 up till today, it's been going up. Anyone who tells you the planet's not warming, there's your data. You can't argue with the data, it's going up. Now it jumps all around for all kinds of different reasons on a short time scale, but on the long time scale, it just keeps climbing. One of the reasons that it jumps around is that the heat that we're adding by putting more greenhouse gas in the atmosphere is not all staying up there. Some of that heat goes to other places. In fact, almost all of it is going into the oceans. The oceans are massive heat sinks. They just soak up heat. So all this heating that we're adding by putting carbon dioxide in the atmosphere, a little bit of it stays in the atmosphere, that tiny little fraction shown up there. But over 90% of it is going into the oceans and warming up the oceans. And there's exchanges of heat between the oceans and the air all the time. And those happen on all kinds of different time scales based on the way the currents are flowing and so on. And that's why one of the reasons you get a lot of this variation from year to year is the exchanges of heat between the ocean and the air. But the total amount of heat just keeps going up because we keep adding more carbon dioxide to the atmosphere. So there's all kinds of evidence that the planet is warming up. I showed you the data of the land surface air temperature, which is the temperature that you and I experience every day. That's been going up, and we can demonstrate that very clearly with all kinds of measurements from all over the world. We know that the ocean heat is rising, the heat content is rising, and I showed you that's actually where most of the heat is going. But there are lots of other things that you can measure and see this as well. The sea surface temperature is rising. The air above the ocean, as opposed to above the land, that temperature is also rising. The troposphere, that's where we live. That's the lower part of the atmosphere. It's where all weather on Earth is in the troposphere. That's warming up. Humidity is rising, which you'd expect if temperature is going up because more water evaporates. Sea level is rising. Glaciers are shrinking. Sea ice is melting. Snow cover is decreasing. There are countless examples to show you that the planet is warming up. This is incontrovertible. So we're in Florida. So I wanted to show you, let me take a step back. I wanted to show you undeniable proof of global warming. This is what a swimsuit looked like in the 1890s. There's by the 1910s. And if we keep marching forward in time, I see a trend here. We'll stop at 2015, thankfully. So there's your undeniable proof. If you weren't convinced so far, clearly the planet is warming up. Okay, now there's something that we need to get clear. This is one of the biggest sources of misunderstandings with climate disruption. Weather, which is what's outside. Right now I think it's about 88 degrees outside and sunny, which is I guess what it's here most of the time. That's the weather. That's what it is today here. Weather is not climate. They're not the same thing. Weather is what's happening right now outside. You have to average that weather over 30 years to figure out what the climate is. That's how the World Meteorological Organization figures out those normals. When you see the weather report and they tell you what the normal high and the normal low is for a given location, for a given day, that's what they're talking about, is the 30-year average. That's climate. The average thing that happens over that type of time scale. Very easy to get confused. There was a question earlier today about we had this really cold winter. That has nothing to do with it, or very little to do with it. You have to average, if you had 30 cold winters in a row, that would mean something. One cold winter, 2 cold winters, 1 hot summer, those don't mean anything. You have to look over a long period of time to really understand what's happening to the climate. Point number 2, your city is not the world. We're talking about global climate disruption. What happens here in Orlando or in Chicago where I live or anywhere else on the planet is not necessarily representative of the global climate. So we had an awful winter in Chicago, not this last winter, but the one before. It was one of the coldest winters known. And it was caused, in fact, by climate disruption, interestingly enough. But there were people saying, it's so cold, it's this whole cold winter, where's your global warming? We just had to look somewhere else on Earth. It turns out other places on Earth were actually way warmer than normal that year. In fact, 2014 was the warmest year on record. And many of the warmest years on record have been in the last decade or so. So there's really no question that we're warming up. You just be careful not to get confused about what's happening outside now or even this season. You have to think on a longer time scale, and you have to think about the whole planet. And if you don't do that, you end up with a lot of misinformation, like this example. So pictured there is Senator Jim Inhofe. For those who don't know him, he's a Republican senator, US senator from Oklahoma. And he's one of the biggest climate disruption skeptics, one of the most vocal ones. And he walked onto the Senate floor in February and presented a snowball and said, it's so cold outside, obviously the climate isn't changing. So first of all, it was February in Washington, D.C. I'm pretty sure it's cold there all the time in February. But second of all, it wouldn't matter even if it was especially cold that day or even if it was a snowball in April. That wouldn't mean anything about climate disruption because it's just one day. You have to look over 30 years and across the whole planet. What's a little bit scary, by the way, is that's his role in the Senate. He chairs the Environment and Public Works Committee. These are our elected leaders. Okay, so how do we know? So there's no question, I hope, now that we can all agree the climate is being disrupted. The question is, are we sure that it's us that's doing it? So we know that we're burning more fossil fuels, and that's putting carbon into the atmosphere. There's just no question about that. And I showed you that the carbon dioxide is going up. But we can there's a fingerprint that points the smoking gun at fossil fuels. That carbon dioxide that's in the atmosphere, we can do what's called an isotopic analysis on it. Carbon comes in different isotopes. You've probably heard of carbon-14, which is used for dating old archaeological sites, right? Because that's a radioactive isotope. There are 2 stable isotopes of carbon, carbon-12 and carbon-13. And it turns out that plants really like carbon-12. They prefer it over carbon-13. And so plants, when they process the carbon dioxide out of the air, they do photosynthesis, and they grow. They're pulling in extra carbon-12. And those plants die and get buried, or millions of years ago they died and got buried, and those became coal and oil and natural gas. That's where they came from, was plants a very long time ago. So that carbon-12 excess is trapped in that fossil fuel. And so if we're burning fossil fuel and putting the carbon dioxide into the atmosphere, that increase in carbon dioxide concentration we see should have greater carbon-12 concentration over time or less carbon-13 concentration over time because it's coming from those fossil fuels that have that isotopic makeup. And you can actually look at that. There's carbon-13, that's the one the plants don't like, and it's going down progressively for a long time. That increase in carbon dioxide is coming very much so from fossil fuels. This is just sort of a smoking gun proof of that. But there's more. We also know that if we're burning fossil fuels, when you burn fossil fuels, part of the chemical reaction is that you consume oxygen. So if the increase in carbon dioxide is coming from burning fossil fuels, we should see the oxygen concentration in the atmosphere going down. There it is, it's going down, measured at 2 different places, California and Australia. We also know that if the warming that we're seeing is coming from greenhouse warming and not something else, there are people who argue that the sun's output has been increasing and that's why it's warming. Turns out the sun has actually been decreasing its output, so that's definitely not it. But aside from that, if it's true that the warming is coming from greenhouse warming, nights are going to warm faster than days because of this blanket effect. If it was coming from an increased output from the sun, nights and days would warm at the same rate. But if it's because of a better blanket, a thicker blanket, if you will, nights are going to warm faster than days do, even though they're both warming. And the data shows that as well. What's called the diurnal temperature range, that's a difference between the minimum and maximum temperatures in a day, has been decreasing because the nighttime temperature has been increasing faster than the daytime. You can also measure this directly. You can actually put a satellite in space and measure that long-wave radiation that's coming up off of the surface and see how much you're getting coming through the atmosphere that's not getting trapped by the greenhouse gases. And you can measure that 30 years ago and measure it today and see is there more getting trapped or less. If the greenhouse effect is getting stronger because we're trapping more. And you can see that. You can also get on the ground and look up and measure the radiation coming back down from the atmosphere, being absorbed and reflected back down, and that's also been going up. And there's the data showing that. There are other examples too. If the troposphere warms up, the part where we live, that's where we're trapping the heat, the layers in the atmosphere above there should cool, and we can measure that, and that's happening too. Also, if the troposphere is warming up, it should expand, just like I was talking about with sea level. The sea level is in part rising because the ocean is expanding as it gets warmer. The atmosphere, our part of the atmosphere, is warming, so it should be expanding. That's happening too. The layers above are cooling, they should be shrinking. We're seeing that too. Every piece of evidence you look at tells you that this is what's happening. Greenhouse warming is why it's warming, and we know that greenhouse warming is coming from our burning of fossil fuels. It's us. Despite that fact, that's the science, when you poll the public, it's a little disconcerting what you find. So this Gallup periodically polls the public and asks them questions about, well, obviously many things, but one of those is global warming and climate change. And here's a question that they've been asking for a long time about whether people think the effects of climate change have already begun, will happen soon, will never happen, and so on. And what's a little alarming is that despite the fact that the scientific evidence in support of the fact that this is happening and that it is us has been growing mountainous over time, you can see that since the 90s, these poll numbers have basically not changed. They jump around a little bit, but about 1/3 of the people out there think that this is never going to happen, or at least not in their lifetime, even though it's already happening. So there's a disconnect between the public understanding and perception and the scientific facts. You can see it here too. Here was another question about if people are personally worried about climate change. Is this something that they feel they're concerned about? And you see that number jumps around, but it also has not been going up over time. It sits right around 50%. That's going to have to change. What's interesting is to contrast this with what scientists think about climate disruption. So there's this great study that was done by actually a guy who's a friend of mine at the University of Illinois at Chicago, Peter Doran. He and his student, he's an environmental and earth sciences professor, and he surveyed the community, a big survey, and he asked all kinds of people in the public, general scientists who aren't climate scientists, so biologists and physicists and chemists and everything else, and climate scientists. The question, a very simple question, basically, do you agree with the statement that the planet is warming up and that it's being caused primarily by our burning of fossil fuels increasing greenhouse gas emissions? So that's called what's known as like the consensus view. And so the question is, yes, do you agree with it? No, do you not, or are you not sure? And you can see here that he broke down the results based on the type of people he was asking the question to. The general public, as I just showed you also from the Gallup polls, right around 50% of people think this is happening. But the general public has not been sufficiently educated on the topic. If you go to scientists, that number goes up dramatically. But interestingly, if you go to climate scientists who are actually active in the field, publishing papers in climate science, that's that dark bar on the side. Look how high that is. In this one, it's 97%. It's almost impossible to get 97% of scientists to agree about anything. Trust me, I work with them every day. That's amazing. This is like the highest degree of consensus you'll see in a field about just about anything, other than maybe the basic laws of physics. This is essentially everybody. And in fact, that was in 2009. More recent polls actually show higher numbers. It's now 98 or 99% of the active climate scientists who are on board with this. So anyone who tells you there's a debate in the scientific community is just wrong. The people who know what they're talking about all agree. Now, another way you can measure this is scientific societies. So scientists organize themselves into societies based on their discipline. There's the American Chemical Society for chemists and the American Physical Society for physicists and so on and so forth. And these societies are all over the world. And many of these societies have statements about climate change, climate disruption. And if you look at which ones have statements that say this is happening and that it's caused by us, here is probably a partial list. And I've hunted, and I can't find any, not one, that has a statement saying the opposite. So there just simply is consensus. We should stop this charade of a debate. There is no debate. The facts are clear. Okay, so that's the problem. My talk was titled Climate Disruption, What We Can Do. So I'll finally get to the what we can do. So I like this quote. This quote says, "The Stone Age didn't end because we ran out of stones." And you'll notice who said this. It's been attributed to other folks, but I'm pretty sure this is the first guy who said it. He was a Saudi oil minister, and he's referring to fossil fuels here. What he's saying is, our fossil fuel age is not going to end because we run out of fossil fuels, which would happen someday if we kept extracting them out of the ground. It's going to end because we have better options in front of us. And the Saudis know this, so why do we not know this? So what can we do? We basically have three different approaches we can take: mitigation, geoengineering, and adaptation. Those are our options. And I just found this picture yesterday. None of these options is going to be easy. They're all hard. So let's look at them one at a time. So adaptation, we heard a lot about this from John Eglander in the context of sea level rise. This is something we're going to have to do. We have no choice. We've already warmed up the planet a fair amount, and it's going to keep warming no matter what we do to some extent. Even if we stop burning fossil fuels, it's still going to get some amount warmer, and they're going to have more ice going into the oceans, and that's going to raise sea level, and we're going to have to deal with that no matter what. No matter what we do, we're going to have some big problems in front of us. As I told you, the weather's already changing. So what we're going to need to do is adapt. We're going to need to plan for these impacts. We're going to need to move people away from those low-lying areas. In places where it'll make sense, we can build seawalls. We're going to need to be more prepared to respond to major natural disasters like big hurricanes hitting populated areas and so on. We're going to have to do all of that. We have no choice. So that's just a given. A crazier thing to consider is geoengineering, which is using the planet Earth as a laboratory. The idea here is that on a global scale, if we want to stop this warming from happening, we could suck somehow carbon dioxide out of the atmosphere on a massive global scale, because that's what's causing the problem is the carbon dioxide, right? So if we could pull it out of the atmosphere, that would lead us to warm less. But to do that on a massive scale, you'd have to do some pretty crazy things, like growing huge amounts of algae in the oceans by fertilizing them, or developing new technologies that don't even exist today to capture, just man-made technologies to capture carbon dioxide out of the air. Another idea would be to keep sunlight from actually getting down to us in the first place. And there's various ways to do that. You can put mirrors in space. Sounds crazy, but people are talking about it. You could make rooftops everywhere white to try and reflect more sunlight back up, like the sea ice. You can make the oceans themselves. I mentioned oceans are dark, they absorb lots of energy. If you have machines making bubbles in the oceans, bubbly water's whiter, right? It's going to reflect more light back up. These are all ideas that maybe they could work, but they're on a massive scale doing something to our planet, and I guarantee you every single one of those would have all kinds of unintended side effects that would probably, in many cases, be worse than the problem we're trying to solve in the first place. I don't think this is the idea that we should be following, geoengineering. So I mentioned we have to do adaptation. I sure as heck hope we don't have to do much geoengineering. The only option left is mitigation. And the way you mitigate the problem is you reduce your emissions. We stop putting so much carbon dioxide into the atmosphere. So what can we do? Where can we get our energy from? So I have here a series of boxes that I've scaled in size to represent how much energy you could ever get worldwide from these different sources if you did it everywhere you could feasibly. And don't take them as precise numbers, they're plus or minus some amount, but they're approximately correct. So even if you got all the geothermal power you could everywhere on the planet, it's going to be a pretty small contributor. So geothermal energy, that's where you're drilling through the crust of the earth and getting to that heat that's down under the crust and using that heat to boil water, to make steam, to turn turbines, and make electricity. And you can do that where the Earth's crust is very thin. So in Iceland, for example, they get lots of energy from geothermal. But and I've nothing against geothermal. It's a great energy source. We should do it everywhere we can. But even if you did it everywhere you could, we're talking about a small contributor to our energy mix. You notice fossil fuels are a massive resource. So yeah, we're probably going to run out of oil, at some point in, some of the people in this room's lifetime or their children's lifetime. But there's enough coal to last maybe as long as 1,000 years. We're not going to run out of this stuff anytime soon. So we could power the entire planet with fossil fuels if we wanted to. That's essentially what we're doing today. You could scale up nuclear fission to power the entire planet. But to give you a sense of the scale we're talking about here, to get to that 30 terawatts, you would have to build a new nuclear power plant every day, starting today, all the way to the year 2050. That's a lot of nuclear power plants. And as we heard from Helen, there are some reasons why maybe we don't want to be thinking about nuclear at anywhere near that type of scale. So this is the box that we filled today. I gave you some numbers at the beginning. I said we use 18 terawatts worldwide today. That box is an 18 terawatt box. And so how are we filling that box today? Where does our energy come from? It looks like this. The black part of that box is the fossil fuels, coal, oil, natural gas. And you can see almost all of our energy is coming from those fossil fuels. Next would be nuclear and hydropower, and then pretty much inconsequential contributions from these other energy sources. But I'm not so much concerned about today. Well, I mean, I'm concerned about it, but I can't do anything about it. It is what it is. My question is, I have a 12-year-old I mentioned. What about when he's middle-aged, in the year 2050, when we're going to be using twice as much energy? 30 terawatts is the projection. Where are we going to get those 30 terawatts? That's a 30 terawatt box there. Again, almost twice as large as today. And there are lots of folks who are trying to project what our energy mix will look like in the year 2050. And there's, of course, all kinds of different opinions of what it might look like, but a general consensus picture of what people are projecting it'll look like is this. So this is a frightening projected scenario. That looks almost like it does today, right? Just everything is scaled up much bigger. So everything grew because we needed a lot more energy, but that box is still almost all fossil fuels all the way out in the year 2050. In fact, it's more fossil fuel use than we're using today, not less, because we need so much energy. This is unacceptable. The hidden costs associated with that energy use will ruin us all. This cannot be the scenario in the year 2050. So what can we do? So let's just do a hypothetical exercise. Let's say we didn't want to use any fossil fuels by 2050. And my guess is that no matter what we do, we will be using some still in 2050, but let's just say, hypothetically, we didn't want to use any. And let's say, following Helen's advice, we want to avoid nuclear as well. How much can we get from the renewable energy sources? If we do them everywhere, we get all the wind energy we can, all the biomass, all the geothermal, and so on. I'm going to empty those boxes out. How much energy can we get? And you notice we're coming up short. But also you'll notice, if you were paying attention, there was one box that I didn't show you yet, which was the solar energy box. So the question is, how big is that one? So I'm going to go from boxes to circles. So that is a circle on the left side. It's just too big to fit on the screen. That's a big circle. And that is the amount of energy that hits the surface of the Earth from the sun all the time. Huge amount of energy. It's actually enough energy hitting the surface of the Earth in 1 hour to power the entire planet for 1 year. But that's not a useful statement, because you can't capture all of the energy hitting the surface of the Earth. So the question is, how much could you actually get? What's feasible? So this is kind of a back-of-the-envelope estimate of what's feasible, what we could actually get. So the first thing I'm going to do is throw out the oceans. We're not going to cover the oceans with solar panels for all kinds of reasons. So I scale down to land area. But of course, we can't cover all the land area with solar panels either, right? Because we need farms and all kinds of other stuff. So what's a reasonable amount of land that we could cover? I'm going to say 2% is a reasonable amount of land. That's a lot of land. In the United States, roads cover roughly 2% of the land area, so you can get that in your head. We're talking about a lot of land, but it's possible. 2% of the United States would look like that. Now, I'm not saying we're going to put all the panels in west central Kansas, but that's 2% of the United States, of course, spread out around. So that's feasible, I think. But we have another problem. You can't convert sunlight to electricity with 100% efficiency. There are fundamental losses in that process. The basic laws of thermodynamics limit you to about 30%, is about the best you can do for a power conversion efficiency. You can buy panels for your rooftop today, commercially if you want, that do it at 20%. So that's a commercial product today, 20% power conversion efficiency. I'm going to be much more conservative. I'm going to say 12%. So that's a very realistic number for an average power conversion efficiency. But now we're down to that measly little circle, right? That tiny little circle there compared to that massive one we started with. But that tiny little circle is that yellow box. So the feasible solar energy supply, what we could actually get, is more than 2 times larger than the total projected global energy demand all the way out in the year 2050. In fact, it's bigger supply than the projected global energy demand in the year 2100. So this is really an inexhaustible energy source for the foreseeable future. Now, I don't say that to say we should get all of our energy from solar energy. In fact, that would be a bad idea. You want an energy mix for all kinds of reasons. For one, that the sun does not shine all the time. Well, it shines all the time, but it doesn't shine on you all the time. So you need a mix of energy sources, wind, and you need baseload power from hydropower and so on. But it's got to be a much, much bigger piece of the puzzle than it's projected to be, and a heck of a lot bigger piece than what it is today. And by the way, it's not surprising that the solar resource is so much larger than things like wind and biomass and hydropower, because those really are solar energy going through extra steps. The reason the wind blows is that the sun heats up the air and it starts to move around through convection and so on, and that creates wind currents, some of which you can capture with turbines. So of course it's going to be less energy overall because it's going through extra steps. Same thing with biomass. Biomass is using crops that turn sunlight into chemical fuel by photosynthesis, extra steps. Hydropower happens because the sun evaporates water, mostly from the oceans, goes into the air. Some of that rains down on high elevations and comes down rivers that we can dam up and get hydropower. Solar power going through extra steps, so those boxes are smaller, not surprisingly. So why are we not all using solar energy today? That's actually a complicated question, and there are lots of answers to it, but one of the big ones is this one, and this is really a question about tackling climate disruption in general. It's a principle in economics called the tragedy of the commons. And what the tragedy of the commons is the depletion of a common resource by individuals acting in their own rational best interests, even knowing that they're sacrificing their long-term interests. Let me give you some examples. Overfishing. So overfishing happens because these fishermen go out and they want to get as many fish as they can to make as much money as they can so they can make a living. So they all go out there and they get too many fish, and then what's going to happen? There's not enough fish for any of them, and then they're all out of business, right? But each one of them they're not stupid, right? They're getting those fish because that's how they make money. They're doing it in their own individual best interest in the shorter run. Another example would be the use of freeways. Freeways seem like the best way to get to work, right? It's a big highway that takes you straight there, but when everybody does that, it looks like this. Depletion of a shared resource. Each one of those individuals is making what seems like the smart choice, taking the most direct path to work, but when everybody does it, it makes it bad for everybody. Another example would be public restrooms. I won't go into the details on that one, but you get the picture. So what this means is that we must act collectively. You can't rely on individuals or individual nations even to make the right choices here, because if each nation is only looking at its own interests and only in the relatively short term, they're not going to change their energy mix on the type of scale that we need to do or on the time scale that we need to do. We need to do it together. And people are trying to do this. You've probably heard of the Kyoto Protocol, the climate agreement that happened back in 1997. What you may not know is that actually these things happen every year. The UN holds one of these climate conferences, and it actually started before the Kyoto Protocol. So we've been making efforts to do something about this for a long time, and we're making progress, but it's slow progress, unfortunately too slow. So we need folks like you to start pushing some more energy behind this and do something about it on a time scale that's actually going to make a difference. So what can we do? Well, it's the sort of things that the Kyoto Protocol tried to do. So the problem is that all the carbon dioxide we're putting in the atmosphere. And I mentioned that the reason we're burning those fossil fuels, well, you told me, was because they're cheap. Now, of course, if you count for all those hidden costs, they're not cheap. They're really, really expensive, right? And solar and wind and everything are actually much, much cheaper when you look at the whole picture. But nobody looks at the whole picture. They just look at what they're paying the electric bill to the company. And in that context, at least in places that aren't very sunny, things like solar don't look as competitive. But what you can do is you can take that cost, that hidden cost, and monetize it, put it in front of people so they can see it. For example, with a carbon tax. So if you had to take that social cost of carbon that we're all paying but we don't realize and put it on your electric bill or at the gas pump or whatever, I guarantee you're going to start looking for a different way to get your energy because suddenly it's going to look a lot more expensive to be getting it from burning the coal. So that lets the market take care of the problem for you. Cap and trade is another way to do this. This is where you decide this is how many carbon emissions the planet can tolerate, total, and then you break that down and say, this nation is allowed to emit this much carbon. And then within that nation, they'll give each company, they'll say, you're allowed to emit this much, and you this much, and you that much. And then what happens is, if a company can become more efficient and use less fossil fuel, they can sell that right to emit to someone else, and they make money. So it's good for them. But overall, the system keeps getting more efficient that way because everybody wants to be more efficient and make money. That's what cap and trade's all about. We also can just be a lot more efficient. So energy efficiency is the cheapest energy source. Those boxes I showed you, I didn't show you a box for energy efficiency. It's really an energy source, even though it's us using less energy, because we don't have to make the energy if we're not using it, right? So it's like a source. And there's so many ways that we could be more efficient. It's not just switching to LED light bulbs, but driving more efficient cars, carpooling, all the stuff you guys already know. We have to do all that, and that is the cheapest thing to do. We should do that first, absolutely, as much as possible. But even if we're as efficient as possible, that doesn't get us there, not even close. We have to do that and a lot more. And the last step here is we really need to support the research and development infrastructure of this nation and globally as well. Because we're going to need some new technologies to get us around this problem in all kinds of arenas. We need to do better modeling of our climate. We need to do better forecasting of how it's going to impact fisheries and all other parts of our economy. We need to develop lower cost solar technologies, more efficient wind turbines, cars that get more miles per gallon. All of these things require research and development. And the way it works now, years ago, companies used to do a lot of that R&D. But most of the industrial R&D infrastructure in the United States, at least, is gone. The great research labs, Bell Laboratories, and so on, these things are basically gone. So who's doing all that research? Government-supported research at universities and at national laboratories, and we need to support them because they're the ones developing the solutions to these problems. So I like this picture. That little tiny sliver of blue that you see there, that's our atmosphere. This is obviously a picture taken from space with the sun just on the other side there, just peeking up, so you can light up the atmosphere like that. And I like this picture because it really shows how delicate and razor thin that atmosphere is. It looks big to us when we look up in the sky. It seems to go on forever, right? But it's actually a really delicate, very thin envelope around us that allows all of us to live. And even though we're only talking about parts per million of CO2, and the atmosphere looks so big, we are changing it. We are putting carbon dioxide in the atmosphere, and it is changing our climate already, and we'll be doing much more so in the future. And that's a very delicate blanket that we all need to survive. I think we need to take a little more care for it, respect it a little more. And let me just end with this sentiment, which is there's a lot of debate. It's unfortunately become politicized about climate change, climate disruption, where people think, if you support it, if you believe in it, you're a tree hugger. First of all, believe in it doesn't even make sense. It's there whether you believe in it or not. It's happening, right? But it doesn't matter what party you vote for. It doesn't matter what church you go to or synagogue or mosque or temple, or if you don't believe in God at all. There's something that we all agree on, and that is that we want our children's lives to be better than our own, or at least as good as our own. And that future is at risk because of what we're doing to our planet. So I think it's time for us all to get together and solve this problem. And I'd be happy to answer any questions you have.
During the previous break, I heard a discussion outside, a couple of people saying that they would never support a carbon tax. And I think the tax word is a little scary. So could you talk about fee and dividend as a possible alternative to carbon tax?
So I should say I'm not an economist with no financial training of any kind. I think what's important is to capture the social cost of carbon. I think if you present it to people as a cost, then it's easier to understand because you're paying it anyway. This is the whole point. Yes, countless think tanks out there that I'm sure can come up with the right words to use, but it's the principle of the thing. We are paying that cost already. We just don't know it. If we knew it, we would make smarter choices. People aren't all as stupid as we think they are. We'll make the right choice if we actually see what it costs to be burning that carbon. And the way you do that is you monetize it. You have different options. You can put solar panels on your house and pay 10 cents per kilowatt hour for your electricity, or you can, with that social cost of carbon added, you'll be paying 20 or 25 cents per kilowatt hour, and what are you going to do? Obviously, you're going to put solar panels on your house. It just makes the decision so much easier, and the market solves the problem for you from within, rather than trying to enforce it from above and saying, you've got to stop burning that coal.
I got involved with the issue of global warming because I heard about the fact that at wind farms, the EPA decided not to, for 30 years, they're not going to fine the companies for the death of the birds that are there. And that was very unusual. There were protests by animal welfare organizations, but it basically, there will not be penalties on people who kill preserved, protected, endangered species. I also found out that it's very hard now to judge the cost in terms of bird and other animals' deaths. There are about 400,000 in the United States a year. There are hundreds of millions of birds that have been killed. And that troubles me deeply.
Sure.
Okay. Also, you're talking, that's the wind farms, these miles and miles of killing fields. Also, in the solar tower, this 70 stories high, that they cost taxpayers $2.2 billion. Before it was even opened, there were quite a number of incidents of birds' deaths because they flew into the mirrors and were then fried at 1,000 degrees when they fell. And also, the environmentalists didn't realize that that the birds migrate in migratory fields.
Sure. Okay. I think I get the gist of the question.
Okay, but let me just say the rest of it. That's what troubled me. My heart aches. My heart breaks for that. But I then, because of that, I looked into the research myself. I am a Ph.D. from Cornell. I didn't see at all any consensus. I think it's very simplistic. And so when you speak, which is well presented, I don't buy it at all. And somehow I feel that you're trying to sell it to me. You're discrediting anybody who doesn't agree with the government approach. And that troubles me greatly because as a scientist, science is so much bigger, so much grander, so much more intricate, so much more, the universe is so complex, and to sort of then pin it on the fact, well, it's carbon emissions and we got to change it and everything has to happen is an insult to my intelligence, and I think and travesty to the world.
I think I understand the question. So let me address the wildlife impact first. So any technology that is rolled out on the kind of scale that energy technologies roll out at are going to have negative environmental impacts, unavoidable. Another one that she didn't mention is solar farms. Great place to put them. Big utility scale solar farms would be out in the desert, right? Because there's lots of sunshine and there's no people there, so it's not in the way. But there are other things there like the desert tortoise, and the desert tortoise is an endangered species, and if you build a bunch of solar panels over their habitat, you're going to kill desert tortoises, and that's obviously not a good thing. People know this. The people who are in the renewable energy community are motivated by this problem. They don't want to kill birds, right? But you have to consider what are our alternatives. We need that energy. We have no choice. That energy is going to be used no matter what we do. So where are we going to get it from? If it's not going to be from wind and solar, it's going to be from coal and natural gas. And if we do that, it's going to cause all the problems that I just discussed. So yeah, there's going to be some negative environmental impacts, and we try and minimize those. So for example, in siting solar farms, the Bureau of Land Management, it's the part of the federal government that owns lots of land, especially in the Southwest. They would like to lease that land to power companies to build a utility scale solar farm so that they could get more renewable energy out there. But to do so, those companies need to do an environmental impact analysis, and they look at all kinds of stuff. So wildlife impact is just one. You look at how you're affecting water resource issues. You look at paleontological questions, whether you're infringing on Native Americans' rights, aesthetic things. You wouldn't cover the Grand Canyon with solar panels. I mean, there's dozens of parameters that are analyzed. And what they do is they identify the regions where you'd have the smallest environmental impact, and those are the places where you get the least to build the utility scale solar farm. And it may still have some small negative environmental impacts, but I guarantee you it's a hell of a lot better for the environment than the alternative, burning the coal, which causes all these other problems, not just climate change, but all the other problems, those miners dying under the ground, black lung disease that coal miners get. I mean, it's just an awful, dirty thing. The asthma attacks, everything else. There are a million reasons, even beyond climate disruption, to stop using fossil fuels. They're just dirty, terrible things. And in fact, they're really useful for other stuff. Think about how much stuff that we use that's made out of plastic, or our pharmaceuticals that we use to treat our diseases. Many of these things actually come from petrochemicals, from oil, originally. We're burning that stuff. It's stupid. This stuff is enormously valuable for us, right? We're going to need that stuff to make the materials and other high-value commodities that we need. We shouldn't be burning it. We should be using small amounts of it to make the stuff that's really important to us for our lives and get our energy from somewhere else. Now, in terms of the consensus question, I mean, I showed you the data. The fact is that the temperature is rising. That's undisputable. And the fact is that we can measure directly that temperature is rising because of the greenhouse effect. And we can attribute that greenhouse effect increase specifically to carbon dioxide coming specifically from fossil fuels. All of that is inarguable evidence in the scientific literature, peer-reviewed by literally thousands of people through the IPCC process. So there's really just, as I showed you, no debate in the community. There's no conspiracy. 97% or 98% of climate scientists don't all get together secretly in some basement somewhere and like come up with a way to fool the whole world about what's happening. They're scientists. They're trying to figure it out. We would love it if this were not what was causing it. If there were an answer that didn't involve changing our entire energy infrastructure, that would be awesome. Unfortunately, this is the truth. This is what we're faced with, and we need to face it.
Steve, have the externalities of fossil fuel been actually worked out? And if so, it would be fascinating to add that amount that you've been talking about onto the electricity bills. Has that work actually been done? I'd love to know, because I'd use that.
Yeah, so there are a number of economists out there who specialize in this topic, and they try and come up with what is the social cost of carbon per, they do it per ton of CO2 emitted into the atmosphere. Scary that the unit is tons, but that's what it's in, because we're talking about a gas, which doesn't weigh very much. And those numbers range over big ranges. Of course, economists, just like anyone else, are going to have their own, opinions and ways of calculating. And then ranges everywhere from sort of in the range of maybe $10 a ton up to like $100 a ton, and you'll get different economists making different arguments. And of course, those numbers will rise over time too, because as these effects become more severe, the costs become more severe. By the way, the costs we're talking about are in the trillions of dollars associated. That's what the economic cost is projected to be by economists on this. And incidentally, the insurance companies know this too, and they're looking at this very seriously. And these are not tree huggers, right? These are people who care about dollars. And they know that this is going to be a huge cost for all of us, and they're looking at it very seriously.
Yeah, so I think when we talk about this, we should give an amount and say $50 a ton or whatever.
Yeah, so that's what I'm saying. People have done that, and there have been proposals put forward by various governments around the world with specific numbers in them. So when you draft legislation, you usually put a number on it, whatever that is.
So we need to actually implement that by law, don't we? So people understand how how expensive electricity actually is from fossil fuel.
That's right. That's the whole idea. Is we're paying it. It's not costing you any more to put that cost there. You're paying it. You're just paying it through ways you don't realize. We're all fools, right? We're paying the money for some other way. It would be like going out and buying a TV for $200 and then driving down the street and giving another $200 to the dentist. It just makes no sense. We're spending all this money that we don't even realize to other sources.
What would you recommend the average person to do to help with this? I was thinking solar panels, but they're very expensive. My in-laws got them almost 10 years ago, and I'm sure it's gone down, but I think they paid $180,000.
It's gone way down, I can tell you that.
That's good. So about roughly how much for a 3,000 square foot house would solar panels be? And if you believe in electric cars, I've also seen data that the batteries in Priuses to make them emit are more dangerous to the environment than the savings of not emitting the carbon fuel.
I
Is
think
that true?
I think the analysis you're referring to is back when they used nickel metal hydride batteries. So I used to drive a Prius which had the nickel metal hydride batteries, and that was not a very environmentally friendly process to get those materials. They're now lithium ion batteries, which aren't as bad for the environment.
Are they made, though? I heard they were made overseas, and then the shipping to ship them over
Yeah,
here.
so the right way to analyze that is doing what's called life cycle assessment, where you look at the materials all the way from the extraction of the raw materials from the earth, that's where our raw materials come from, right? We mine the materials and then you process them, and manufacturing and transportation, all of those things have environmental impacts and take energy and everything. And there are all kinds of experts out there, not including myself, who know how to do that quantitatively, to really say how do you quantify all those different environmental impacts and how much energy went in and everything, so that you can find where the problems are and fix them. And there are people who do that for all these different energy technologies, from electric cars to solar panels to everything else. Now, what people can do, we're actually going to have a panel, I'll advertise later this evening. Helen and John and myself and another author are on a panel later this evening called Plan B, where we'll address exactly this, sort of what are the things that people can do. So you'll get a broader answer to that if you come to that panel. But just quickly, to answer your question about solar panels, which is just one thing to do. So it doesn't cost you $180,000. Now, if for a typical home, my parents actually just put solar panels on their house last year, and you're talking now in sort of the $15,000-ish range for your typical American home. And there are lots of subsidies available to help you with that. But I want to add that there are other models. You don't necessarily have to put the panels on your house. So one thing, some homeowners just can't afford that. But also, some homes just aren't conducive to it. You might have trees that shade your roof, for example, and so you can't put solar, but you don't want to cut the trees down. That would not be good, right? But there's a new model that's really emerging called community solar. And I really like this idea, and it's taking off from a business side as well, which is you get people in a neighborhood collectively to own subscriptions to a solar farm that is in like a parking lot or something in the neighborhood. So a nice open space where you can put a nice big array, and then you also get economies of scale. It costs less per panel if you buy more of them at a time. And then people can subscribe to it just like you would to the power company. Instead, you're subscribing to the power from that solar farm. So you don't have to buy the panels yourself. You're just buying the electricity, but you know it's coming from those solar panels. It's a way to, it's just one of the economic models that's out there. There are countless other ways. There are people who looked at making it more affordable for homeowners to do this. There's a big company called Solar City, for example, where they own the panels. Even though they're on your house, they own the panels and you buy the electricity, things like that.
Great. And then yay or nay on the Prius? Yes?
Any car that gets higher miles per gallon is going to, in net, be beneficial, but you're absolutely right. Just like with food, you want to be local, right? It's better to have things that are manufactured closer to you and that use the smallest amount of, toxic materials. And it's not always the materials in the thing itself that are toxic, but sometimes the process of getting those materials involves toxicity. So a classic example is gold. Gold is completely non-hazardous. You can eat gold and it won't hurt you, literally. I mean, people in fancy restaurants, they do eat gold, right? But to mine gold, you have to do some bad things to the environment. So gold, even though in and of itself it's not toxic, has a toxicity effect on the environment. And you can figure that all out when you do this life cycle assessment I was referring to. Okay. There's a whole body of literature out there about that if you're interested.
Okay, thank you.
Any other questions? Okay, thank you.